I am Dr. Prateek Shah, and I am basically stationed in India. I am working as an associate professor in the mechanical engineering department in one of the premier engineering colleges of India. And just to brief about myself, I hold a PhD degree that is basically a doctorate degree in mechanical engineering. Have got around 25 years of teaching experience with more than 6 years of research experience. I have published more than 30 research papers in international journals of international repute, in conferences, in journals, in Q1 journals. There are many of my papers which have been designated with an impact factor of more than 3. Recently, I have also been granted 2 patents for my inventions. At some point of time, I would like to discuss about that at a later stage. Today is not the right time to do about that. At present, I am guiding 3 research scholars. One of them is recently in the EIT, and I am reviewer of many reputed journals. And major areas of interest is computer-aided design, computer-aided manufacturing, computer-aided engineering, manufacturing in such. And I am also very much interested and work on solid state welding processes like friction stir welding, simulation of manufacturing processes like welding, etc. So once again, I warmly welcome you all to this presentation. Today's presentation will be basically highlighted as the theme indicates. It's about computer-aided designing and manufacturing. So I would just like to start my presentation with a few slides on Industrial Revolution and Industry 4.0, thereby depicting the role of CAD, CAM, and CA in Industry 4.0. We'll we'll have general discussions on various geometric modeling aspects of a CAD software, be it any software, followed by computer-aided engineering. I will also brief you something about the CAD data exchange standards, which are available worldwide and which are adopted by most of the modeling as well as analysis softwares, followed by a brief introduction about computer-aided manufacturing with a case study presented in form of a recording of my screen. In view of time constraint, I will be just sharing you that. And if I don't get time, I will be just sharing you the SharePoint link so that you can do up with that at a later stage. So with this basic introduction, I would just like to move ahead with the introduction, that is industrial revolution and what at present we are undergoing in the revolutions in as far as the industrial revolutions are concerned. As you are all aware, basically we are at present undergoing industry 4.0. Shortly, there will be introduction of industry 5.0 also. But to start with, industrial revolution first took place in the 18th century when there was invention of steam power, when there was invention of the steam power, and the manufacturing process just took a kickstart, followed by industry 2.0 when basically invention of electricity took place and there was invention of mass producing and assembly line machines. Industry 3.0 in the mid 20th century when tools like ICT came into picture with automated machine tools like automats, single spindle, multi spindle automats, along with various other CNC machine tools. And at present, what we are witnessing is Industry 4.0, wherein we talk about advanced robotics, we talked about basically big data analytics, intelligent machining, intelligent machine tools. We talk about IoT and IIoT, that is Industry Internet of Things. So, with this basic introduction about the Industrial Revolution, I would just like to throw some light on the existing scenario of Industry 4.0 and where exactly CAD can fall into this domain of Industry 4.0. As you are aware, basically Industry 4.0 comprises of various aspects of robots, simulation, the Internet of Things, the industry Internet of Things, augmented reality, cloud computing, editing, manufacturing, and artificial intelligence. These are basically the working blocks of Industry 4.0. And I won't be going into the much details as we will be specifically concentrating ourselves on CAD and CAM and also simulation. So when we talk about this Industry 4.0, where exactly CAD/CAM fits into, I wanted to just bring that into account, and so I brought up these slides. Basically, when we talk about Industry 4.0, it is all combination of Internet of Things, that is then artificial intelligence and machine learning, robotics, data analytics, or you can call it as big data analytics, cloud computing, AR, VR, blockchain, additive manufacturing, and system integration about all of this. So basically, CAD/CAM falls into the domain of additive manufacturing and AR, VR, that is augmented reality, virtual reality, and some of the portion of CAM and CAD also falls into robotics. So combining all of this, basically Industry 4.0 works. Industry today, as you are aware, are striving to implement Industry 4.0 due to varied advantages of the system, due to many other manufacturing expectabilities and many other incentives that various governments provide for implementing Industry 4.0. With this basic introduction and with the domain in which CAD/CAM CAE falls under, with that basic introduction, I won't be much touching about Industry 4.0. We can always talk about it at a later stage, but I would like to just focus on CAD/CAM and CAE. CAD/CAM and CAE, as you are aware, are basically the buzzwords in industry today. And it is just because of the advantages that they derive in implementing it in any manufacturing conditions, be it manufacturing, be it an assembly line, be it an core engineering company, anything like that. So this in nutshell is basically a wheel cycle of SIM or computer integrated manufacturing combined. CAD, CAM, and CEO. Normally, people term them as CAE or CIM, that is computer integrated manufacturing, where CAD is basically use of computer systems which assist in creating and optimizing of the design. Whereas computer-aided manufacturing showcases its capability in machining, wherein computers along with CNC machines and robust machines are used for manufacturing multi-complex tasks or jobs or manufacturing jobs with very high precision or very high tolerances, like applicable to many aerospace industries. Whereas computer-aided engineering is the use of computer software to analyze the task or analyze the particular domain, or it is basically used as a simulation tool and optimize products. We will be going into the details of each of them. So with that basic introduction, I would like to start with computer-aided design being the first and the foremost tool that has to be applied in computer integrated manufacturing. We all know a computer-aided design is basically automated or design process, which is basically equipped with the help of softwares. Whereas computer-aided designing, when we talk about, it is very important to showcase the features of a design process. Just to brief about this, basically design is an act of devising an original solution to a critical problem with the help of available resources, and which brings out to a product design. It is basically a step followed by the designer in arriving a solution to a technical problem. If you refer standard papers or standard literature available in the open domain, you will find many models or many of the authors suggesting various models of design. But the one that I like the best is the Shigley's model of design, which basically says that any design process starts with the recognition of the need. Recognition of the need means normally a company or an individual do not go for designing of a product just for the sake of designing it, just because designing would involve high amount of R&D cost. So the conventional design, that is conventional design, when I say it is basically without the use of any CAD tools or without the use of computer tools. It basically starts with the identification of the need, followed by the problem definition, then synthesis. Synthesis would involve basically selecting the material, creating drawings or sketches of the product, followed by analysis and optimization. If the analysis and optimization phase passes through the evaluation, if the evaluation is successful, you normally go further. If it is not successful, then we normally go for the change and design, and we again redesign it in order to make a product viable. Whereas when we talk about computer-aided design, the same model, that is Shigler's model, has been modified, wherein the initial two steps would always remain the same. The initial two steps will always remain the same, whereas Whereas the synthesis portion, where normally people used to create drawings with the help of a pencil and with the help of a drafter or a sheet, has now taken up by geometric modeling phase. People use various geometric tools, various geometric tools, various geometric tools like various geometric modeling softwares in order to undergo this synthesis process. So with the advent of this such type of CAD tools, the design has entirely now changed into digital prototyping, and there is nothing like creation of a physical prototype. Previously, before the invent of such CAD tools, people used to create a physical prototype. Either they would use some material like wood or clay in order to create a model, which will basically give you a feel of a model and was used to analyze it. But with the advent of these softwares, basically now people have rushed on to this computer-aided design tools, and with the help of geometric model, they create models. That is the digital prototypes. The analysis phase has again changed up into engineering analysis. So our CAD falls into this basic category. The CAD portion that we are going to discuss will fall into this category. The portion of CAE, that is computer aided analysis engineering, computer aided engineering, will fall into the engineering analysis capabilities. Once the analysis is successful, then normally people go for presentation or the drafting. Uh, just a minute. I would. Maria, how do I maximize my screen? Can you help me in maximizing the screen?
I'm not sure I'm showing it as large as it goes. Let me just
Okay,
see.
no
Okay,
issues,
do you
no
see the
issues.
three dots on the bottom of the
Yes,
page where it
yes,
says
yes.
17 to it says magnify slide only for me, so you can magnify it there. There you go.
Okay, okay, fine. Thank you so much.
You're welcome.
So with that basic understanding, I would just like to bring to your kind notice that how this evaluation of CAT took place and what were the milestones which computer aided design undertook during this past century or past half century. Basically, the advent of computer aided design tool started in the 20th century. In 1960s, there was a basic tool known as Sketchpad, which basically was a 2D drafting or two-dimensional drafting software which came into the market. In 1980s, there was something called AutoCAD, and I would call it as a revolutionary step in computer-aided design, because though AutoCAD was invented in 1980s, still it finds its application widely in industries, because in my basic knowledge, AutoCAD has got no replacement when it comes to manufacturing drawing or two-dimensional creation of two-dimensional drawing, or basically when you want to create manufacturing drawing to supply it to the shop floor. In 1990s, there was invention of solid modeling software, and many companies came out with solid modeling softwares like Katia, SolidWorks, Pro Engineer, IronCAD, etc. In the year 2000, these CAD tools became more friendly and collaborative, collaborating themselves with product lifecycle management tools, that is PLM systems, and product lifecycle management systems were then superimposed on this CAD software to take its advantage in manufacturing also. By late 2010, cloud-based systems came into existence, which would facilitate collaborating your designs with the engineers worldwide. It would also limit the resources that are required on particular CAD workstation, and that were all basically being done with the help of cloud-based systems that came into the market. At present, what we are witnessing is this, that is intelligently connected systems, and we are also using these intelligently connected systems or CAD designs in order to 3D print or in additive manufacturing. They are also basically meant to use for platforms like IoT in order to convert it into industry IoT. Basically, when we are using a CAD software, the outputs can be any of these three. I'm just stressing upon it because the outputs of CAD will be basically inputs to the CAM manufacturing systems or the CAE systems. So output of any CAD software can be a 2D drafting, or that is basically what we call it as a manufacturing drawing. It can be mechanical part drawings or architectural plant, or it can be also electrical circuits when electrical applications are used. It can be in form of any 3D modeling tools like solid modeling, surface modeling, and wireframe modeling. These are all three basically falling into the category of geometric modeling, which I will be shortly covering up in my presentation. It also helps in documentation. Documentation means creation of bill of materials, and GD&T, that is geometric dimensioning and tolerancing. Basically, this software can also be used for render. The rendered model can be used for marketing and presentation purpose also. So in a nutshell, the output of CAD can be any of this. It depends upon the engineer to use the selected feature of that tool. So moving ahead, I will be talking about the 3D model, more of 3D modeling part. We won't be touching the 2D drafting and the rest of the part, just because 3D modeling is widely used nowadays in order to convert it into a usable product, or in order to have it ready to manufacture. So geometric modeling, when we talk about geometric modeling, all those softwares which are available in the market will give you any of these facilities for presentation of your model or a CAD model. It can be a wireframe presentation, it can be a surface representation, and it can be a solid representation. All of them are considered to be geometric models, and each modeling software available at present in the market provides you this all three facilities. It is up to the individual and the engineer to use the functionality of a particular representation as and when needed. But I will just bring a one or two slides which will just basically bring a comparative analysis of all the three. That is the wireframe, surface, and solid modeling. Wireframe basically is a model represented only with the help of edges. There are no surfaces or no solid bound volumes in case of wireframe. It is basically representation, and it has got its own advantages and disadvantages. Second is the surface model, which will be having edges and faces. Whereas the third and the most widely used type of model is the solid model, which has got edges, faces, and also the solids. Wireframe models basically are a skeleton representation. I will just like to call it as a skeleton representation, just because they will be only having lines and edges in order to connect a geometry. This, though, is a solid model. This is not a wireframe model. I have just represented a wireframe model of a solid model. This is basically a nut. The nut has been created in a solid modeling software, and the same representation is done in form of a wireframe. As I told you, wireframe has got its own advantages. The advantages being it is basically very fast to generate a wireframe model. It is very simple and hence it is very fast to generate. Surface and solid modelers make use of generative quick techniques, but there are lot many disadvantage also. As you can see, this is a ambiguous model because all the lines, that is whether it is in the back side of the view or on the front side of the view, they are shown in form of a grid of wires. So normally wireframe models may pose some ambiguity also while representation. You can also see over here where I have just shown you some models being created in a solid and then a wireframe has been created. This this basically is a cube created, but you can see the hidden line views, all of them are represented in form of grid of wires, which is posing some ambiguity. These are few more wireframe models which are depicting. I would just like to bring to your notice that these models have been presented in order to show the application of the wireframe models. As you can see, both of them are complex assemblies. This basically would be a part of a gearbox which has been assembled, and this is a car assembly. If this assembly has to be represented in solid model, then the representation time would be much more. Even storing would be a problem. And normally, hence, when the models are to be transported, they are converted into wireframe so that they occupy less memory. Whereas surface model, as the term indicates, it will be giving you the surface. The surface models find their wide applications in aerospace industries, in automobile manufacturing industries, or say it will find wide application in any sheet metal industry. Any sheet metal component made up of any metal is basically a surface model. Surface model, unlike wireframe, would have surfaces, but they won't have any kind of volume or any field mounted to it. It is widely used for designing of car bodies and interiors of car. They are also used for aerodynamic surfaces. Also, it finds its application in consumer products like you take casing of any appliance, casing of be it be air conditioned, be it refrigerator or mobile phones, all of the casings are basically made from sheet metal and hence they are all designed into surface models. The basic disadvantage of both the surface models as well as wireframe models is you cannot have any kind of mass properties or volume calculated from that. Whereas solid models are the most informative models in my view. They would represent both the surface as well as the internal volume, and hence mass properties can be easily calculated. The greatest advantage to me when we talk about solid models is it will support simulation and analysis. When we talk about simulation and analysis, always a solid representation is basically used. Wherever you need to analyze a sheet metal component, the analysis is always a surface model. But widely, I would say more than 90% of the analysis, engineering analysis done is on is on solid model. These are few solid models which normally are made in various softwares. This is what created in SolidWorks, whereas this is basically created in Creo. Creo was formerly known as Pro Engineer. Many of you might be knowing the software as Pro Engineer. The general advantages that it derives is high accuracy and precision in design. It is very easy to interact with the engineers or it is very easy to edit. It would save a lot of time and it is very easy to integrate with CAD and CE. That is the greatest advantage to me. Whereas digital storage will also provide you facility to store it in digital form, thereby avoiding big drawings to be stored in a store well or in a storeroom. These are major CAD softwares which are available in the market. I have only mentioned a few of them. Apart from this, there are many other softwares. but these are widely used in various parts of the world. I mean, people in North America would prefer more of SolidWorks, whereas in other part of the countries, people are using PTC Creo. CATIA, yes, CATIA has got very good application when you compare it with aerospace components. More or less, all the aerospace companies would be using CATIA because it is more powerful in designing aerospace components, which is basically made from sheet metal. Then there is a software from Siemens, which is NX. Also, Fusion 360 is a very good software. Fusion 360 is a good software when it comes to cloud computing. The results of the CAD are 2D drawings, 3D models. That is already we have talked about this, but now we'll be jumping into this. That is the result. The result of CAD can also be used for simulation and CA. The results of CAD can also be used for CAM and 3D printing. I would just go through your dear all. I will just go through your chats after completion of my presentation, and I will be shortly answering all of your questions. So I now quickly jump to computer-aided engineering, to which normally we also call it widely as FEA or FEM, that is finite element analysis or finite element method. There are many developments into it. There are machines which also processes FDM or FEM, but we will concentrate rather on FEM today for today's presentation. It basically says that when a designer creates a 3D model or 2D drawings, then it is the output of a CAD software. But the engineers would take this CAD platform for analysis to CAE software. Now, what basically the process is, where if you are designing something, once you design it, once you come out with a solid model or the manufacturing drawing of a model or a product that it is to be newly launched in the market, directly one does not go for manufacturing. We have to check that particular design in order to check its validity when loading conditions come upon. So when certain kind of loads come upon that product, we need to check it in engineering analysis that whether it is going to sustain the conditioned load or whether the material or the product is going to fail. Once you decide upon them, if it is going to fail, you need to redesign it again and then come back to analysis part. And if the analysis is successful, then also you directly do not go for manufacturing stage. There would be a small stage of optimization between manufacturing and the analysis tool. So the capabilities of this softwares are to undergo stress analysis, thermal analysis, fluid flow analysis, and they are also capable of doing multi-body dynamics and computational fluid dynamics. So with that, I will just come to the basic introduction of FEA, that is finite element analysis process, how analysis process is now applied in the real manufacturing world. Basically, when we talk about engineering problems, all engineering problems are mathematical models of a physical situation. You all will agree to me. And I will just bring up some few examples shortly, which will just tell you that an engineering problem can be converted into a mathematical problem. And there are two major methods to solve any engineering design problem. It could be either an analytical approach or it could be a numerical approach. An analytical approach, as the term suggests, it is going to give you exact behavior of the system. So if analytical approach is applied, then it is bound to give you 100% accurate results. Analytical solutions, when I say, it is basically with the help of the standard equations, the standard laws, the standard principles available, and the equations derived from that laws and principles. So you will be using the equations derived from those laws and principle in order to design or in order to basically analyze the component. Whereas when we talk about numerical solutions or numerical method, it basically don't give you 100% accurate result. We always say that the numerical solutions will give you approximately exact solution. Approximately exact solution. FEA method is a numerical approach, and hence FEA method will never give you 100% accurate results. But still, it is widely employed in industries just because of the reason that it is capable of analyzing any complex to complex design problem, may it be static analysis or a dynamic analysis or a complex fluid flow problem, a complex vibration problem. All of them can be simulated if the tool is correctly employed. So these are basic applications of the available FEA software: stress and strain analysis, which are normally used for bridges, building, aircrafts, automobiles, etc. The static analysis, when we say static analysis, the load do not vary with respect to time. When we say dynamic, the load will always vary with respect to time. Buckling analysis. There are also non-structural applications like heat transfer, fluid flow, manufacturing analysis, biomedical applications where FEA finds its applications nowadays. I would just brief you about the FEA process. The FEA process basically takes place in three phases. The pre-processing phase. The pre-processing phase will basically define the physics and the geometric model of the component to be analyzed. If this is the component to be analyzed, then I need a CAD software in order to design this. Nowadays, there are many softwares like FEA softwares like ANSYS, which provides you the capability of modeling also. But still, people prefer a pure modeling software, and then they import the modeling software into the analysis tool. The second is the processing part, wherein you need to divide the entire continuum or the geometry into discrete parts like this. The details of this discretization would itself take 4 hours of long lecture. So I don't go into details of this. But the second step, obviously, in any FEA process is to create a mesh. This is generally known as a mesh, wherein the entire continuum is divided into number of elements. And ultimately, you need to analyze this by providing specific inputs to it, specific boundary conditions to it. And the output, that is the third step, is the post-processing step, wherein the output of a FEA software will always be a contoured geometry like this. And it is left up to the engineer to analyze this particular results, because it would really require high amount of engineering. If I am asked that what is the total amount of time taken by each of the phase, then I would say that at present the pre-processing phase for any analysis would take approximately 30 to 35% of the total analysis time, whereas the processing is now done with the help of high-end CAD workstation. So it hardly takes 10% of the overall time, whereas the remaining time is taken to analyze the given results by the software. That is the post-processing part. Just a small case study how everything goes underway. If there is a real-time engineering problem like this, then how do I convert the real-time engineering problem into the mathematical model? Basically, I am supposed to analyze this particular crank of a bicycle. The crank is fixed here over here to the sprocket, whereas the other end over here has a pedal where normally the motorist would be giving the force. So this particular entire system has to be disintegrated into components, wherein I am just interested in analysis of this crank. So I bring out that crank in form of a geometric model like this. This particular portion would be attached to the pedal, whereas this particular part would be attached to the crank. So this is the next step, wherein basically we need to create a model like this. After creating a model, I need to identify the boundary conditions. Boundary conditions here basically is what portion of the entire problem is basically fixed, and where are the critical loads being applied on the component. The loads even that loads can be of many type. It can be of tension, it can be of torsional, it can be compressive load, there can be fatigue load, etc. But over here, the load is applied over here basically, and this particular portion is fixed to the crank. So this is how I bring out the mathematical model out of it. Once that is done, I go in for creating of a mesh. Mesh is basically dividing the entire continuum into number of elements. There are many type of elements available in the available softwares. Software, when I talk about, when it comes to FEA, it is, I mean, 80% of the market share is governed by ANSYS. There are many few software also available in the market, but all these elements are available in any of these softwares. Uh, just to bring out a few examples, say for example, if I am supposed to identify or analyze the rear axle of an automobile, this is a physical problem, and I want to create a mathematical problem of this. The real axle has to be modeled first of all in the software, and then it has to be taken into analysis. But in order to create a mathematical model, I have to go into the physics of the entire system. When I go into the entire system, I know that the entire weight of the automobile is distributed into the front axle and the rear axle. The rear axle, if this is the rear axle, it is supported by the wheels, and the load which is coming on the axle would be something like this. So this is basically a simply supported beam problem, a classic simply supported beam problem, wherein the tires or the wheels of the automobile will act as a support. They are grounded, they are on the ground, and the weight of the automobile will be uniformly distributed on the shaft. So the system was as simple. You need not even create the 3D model of this. Only a 2D geometry would work. So interpreting, what I like to stress upon is interpreting the physical model is very important when you use a software like this. So this would be a very, even if I go into details of this, the load is to be shared between the rear and the front axle. So only half of the automobile load will be coming on the rear axle. So this is how you should depict the physical condition. A small example again, if I am supposed to analyze the arm, a human arm, a person who is lifting a dumbbell, then it can be simply modeled as a cantilever beam, wherein this load is basically the weight of the dumbbell, and this would be a hinge support, not a fixed support, because it is going to rotate over the arm over here. So these are two examples. If time would permit, then I can fetch out many more examples wherein a simple geometry would do the task. But this is how, what I mean to stress is, or mean to say is, you need to control the physical model and convert mathematical model. The last step over here is the analysis part, wherein the software or the tool will do the analysis, and it will come out with some colored contours like this, and it is left to the engineer to analyze this. So interpreting the result is basically not the task of the software. The software will only give you the results, but it is the engineer who is going to interpret this. Various softwares which are available in the market are ANSYS, Abacus, Nissan, Astran, Pastran, Pro Mechanica, Katia, Dyna, Hypermesh. I have listed these softwares because now companies have started giving the basic tools of FEA also. Basically, when Katia was invented in 1990s or Pro was invented in 90s, they only came up with the basic modeling features. But in this competitive market, they now have started basically giving you the basic analysis tools also, that is the FEA tools. But still, there are many limitations and challenges when FEA is talked about. I would rather say that it is garbage in and garbage out. The output is as good as the input. If an engineer is not properly understanding the physical conditions, then there are chances that he will result into a very poor results. The accuracy of the result depends upon the information given. There are many assumptions which are to be made during the process. If possible, we will also have some separate session entirely on FEA, where I would like to cover all of this. FEA at present is applied in all forms of engineering, whether it be a structural, whether it is fluid, whether it is thermal, whether it is vibrational, any kind of tool. To sum up and to end up with a FEA simulation, I would rather say that FEA simulation is like a battlefield. On a good day, you might not lose anything, but on some days, you may hit two mines with both your feet. That is controlling and constraining of the physical situation, and understanding of the constraints is very important, and that too applying into a software. With this basic With this basic understanding, I would just like to take a small topic, that is CAD data exchange standard, just because I told you that these are CATIA or say ProE or SolidWorks are basically used for modeling software. Now there is a need of these softwares, the output of these softwares to be taken into analysis software or CAM software. When I say modeling software, CATIA, Creo, SolidWorks, Fusion 360, all of them are very good in modeling, but they have got limitations when we come to analysis. So a model created into this software have to be imported into analysis software. That is where CAD data exchange standards come into picture. They are basically used for collaboration between different teams and companies. I mean, I would just briefly sum up that when you are using AutoCAD, the extension or the file extension is .wg. When you are using AutoCAD Inventor, it is IPT or IM. If it is part, then it is IPT, or IM is for assembly. When Creo, then it is .prt and ASM. And likewise, now in order to facilitate input of this particular extension files into an analysis software, there are various CAD data exchange standards. These standards work similar to various standards that we talk about. They are acceptable by all the companies, and they are acceptable worldwide. Such data exchange standards are IGES, STEP, DXF, STL, Parasolid. So all of the software, that is CAD softwares, will give you these facilities to convert it into this exchange data formats. So when we talk about this, when a part is created in Creo, then if it is to be imported into ANSYS, it has to be converted into IGES. Some of you might not agree with me, because the latest version of ANSYS are now supporting many of the CATIA files, Creo files, and Inventor files directly. They can import directly without the CAD data exchange standards. So with this, I would come to the last point or the last part of our today's presentation, that is computer-aided manufacturing, wherein computer-aided manufacturing, once the analysis phase is completed, the optimization is done, the analysis is successfully done, there is no failure. Now you can go for manufacturing. So computer-aided manufacturing is something which is done after CAD and CAE. After a product is modeled in CAD, the product design is analyzed and verified in CAE, and the product is now ready to process in the or further proceed in the production stage. So computer-aided manufacturing is applied to create and control programs to run machine tools in manufacturing process. When we say CAM basically has got two parts. One would be a software and second would be a hardware. Software is basically any CAM software. It can be either Master CAM, it can be Siemens NX CAM. There are many customized software which are available with the machines. When I say hardware, these are all CNC machines. So combination of CNC machines along with the CAM softwares basically forms computer-aided manufacturing. In view of the constraint of time, I'm just moving with this slide and skipping it. Anyhow, the presentation will be shared to you. Computer-aided manufacturing, basically, when we talk about it, is very important to talk about two basic machines, that is NC and CNC. NC stands for numerically controlled machine, while CNC is computer numeric controlled machines. NC is now more or less obsolete because it was older and less flexible. NC and CNC, the only change is C, that is computer numeric control. NC did not have a computer, though it had a processor. There was no computer integrated with the machines, and hence it was having many limitations. Whereas DNC is direct numerical control, where you will be having one computer controlling multiple CNC machines. These are basic comparative features of NC, CNC, and DNC. And I would now like to stress upon the workflow of the CAM. CAM basically process starts with importing of the CAD model. As I told you, the CAD model, output of a CAD model can go to either analysis or to manufacturing. So what people do, they import the CAD model from the CAD software and import into a CAM software, which is basically shown over here. The second stage is process planning. Process planning, as in case of conventional machine tool, undergoes various selections of tool, machining strategies, manufacturing sequences, etc. Tool path generation is which is certainly specific to CAM software. Tool path generation is it will show you the motion of the tool when the machining will actually do. It will just give you a simulated view. The simulation will detect collisions of the tool if the program is going wrong, followed by post-processing, that is converting into the tool paths into machine readable codes. Machine readable codes over here means CNC machines will be always understanding a specific type of machine language that is known as a part program, which is combination of M codes and G codes. So quickly, I would just quickly browse to these slides because anyway, I have captured this everything into a small video, which I would like to share with you. So I'm quickly moving due to constraint of time. This is a part program that I'm talking about. This part program is the language that CNC machines understand. And part program is basically the movement of the tool relative to the workpiece. And any part program is combination of two basic codes, G codes and M codes. G are known as the preparatory codes and M is known as the miscellaneous code. I have just shown you a small example of a part program over here. G21 stands for setting up the units in mm. G90 is absolute positioning. M0 stands for tool changing. The machine will automatically go to tool number 1 and select it. M03 S1200 is spindle speed of 1200 in RPM. So the part program is loaded to the machine. The beauty of CNC machines is the part program is automatically generated by the CAM software, as I will show you in the video. It will be directly generated by the CAM software, so you need not worry about that. Only thing you need to worry about this is the simulation and the toolpath. The simulation and the toolpath has to be clearly monitored so that there is no collision. Fix the workpiece on the work table, run the machining cycle, inspection, and then the final product is available. So I will just take 10 minutes more, and I have just created a machining simulation of this particular part. It is basically a part, a rotational part, a very simple part created to just, so that you people experience how actually integration of CAD and CAM works, how exactly CAD tools would be useful in creating the model, and then CAM would do the rest of the task. These are the dimensions of the tool. It is basically a 2-axis job, and it can be done on a CNC turning machine. So there are basically any job that is to be machined can be categorized into two major parts, a rotational part and a prismatic part. Rotational parts are always depicted by a central axis, and they only require 2-axis machining. Whereas prismatic parts are generally created on 3-axis, 4-axis, 5-axis machines, and the most common is the milling of that, milling operation. So I'm just starting this video. Okay. Maria Janu, can you just confirm that the video is working? Can anybody
I
drop me a message?
I can see it. I don't know if there's
Oh,
any sound, but I'm not
no,
hearing
no, it's
anything.
there is no sound. There is no sound to
Okay,
it.
then yes, visually I can see it.
This is the first phase of CNC, I mean CAM, wherein I'm importing a model. I created this model in a specific software and I am importing it into a pro manufacturing model. Once I am importing the model, I now need to create a workpiece because the machine is expected to take the input as the workpiece and then the machining path or the machining processes would machine it. So I'm creating a workpiece. Workpiece obviously would be having more dimensions, that is, it would be plus 5 mm or 7 mm depending upon the availability of the raw material. So once I have imported the part, I am now creating the raw material which I need to feed it to the machine. This is the raw material which is being seen in yellow, and I have made it transparent so that you can see the job inside it. Now it is in green color. The raw material is green color. This has to be machined and the shape has to be formed. So this was my first step, that is importing the CAD model. Now I need to go for the second step, that is the machine settings. I need to define the program 0 and the machine 0. Uh, Many of you might be aware of this. What exactly is program and machine 0? The program 0 is basically the point from where the reference is taken. Because because I need to create I need to create a tool path which will exactly machine the additional and subtract the material and form the job. So now what I am doing is I am just creating a tool path. I am just making the system understands that this is my machining path. This is how my tool should move and remove the additional material. Now comes to process plan. As I talked about, process planning phase involves identifying the machine sequence, identifying the machine tools, and identifying the tools which are to be used. So I am specifying the machine 0. I am saying that this would be my 0 point from where the machining is to be started. I'm naming this cut as rough cut because normally we do two major cuts, the rough cut and the finishing cut. So the rough cut would be having a lesser, I mean more rake angle than compared to a finishing tool. That is what I did. I am now setting the depth of cut. This is the basically depth of cut. I will also specify the spindle speed. This is all the process planning part where I am making the machine ready in form of the sequence of the operations, in form of the tools that are to be used, in form of the geometry which is to be machined. So I have done that. I have created a process plan wherein I have shown the tool. It would be basically a single point cutting tool. This is a APT program. And now I am generating the tool path. This is tool path generation. I said that I have to start machining from this. You have to be careful that the raw material size which you are using in the modeling, the same raw material size should be fixed in the machine. So there you go. You are now with the single point tool and the tool path. This is it. It is now simulating for you. This is the fifth step of the workflow of CAM where you are simulating the entire process. This simulation will show that I have given a 5 mm depth of cut. So after each 5 mm depth of cut, the tool will be retracted back. Again, it will be coming to the new position. It will be coming to the new position. And doing the simulation. I'm sorry for that. I just wanted to fast forward it in view of time. Uh, can you help me to fast forward it? Because I don't have that control. Maria, can you
Let
just
me
use
give it
the
a
slide?
try here.
Yeah, yeah. Because I don't have that control.
To
It's okay
which point do
because
you?
I mean you can just scroll ahead. It's okay if you could not find. That was basically the end of the simulation. The last part was the tool generation and the CNC file. This was, it will take. I will also share this video and that the link can be just given to the participants.
And it's
I'm moving
also in the slide
presentation.
presentation as well.
Yes,
Yes.
yes, yes. It's in the slide presentation. So I am just moving ahead with the presentation. And coming to the last part, that is now what actually the things that I have talked about is already in working since 2020. And we are now in 2025. And as I told you that we'll be moving to Industry 5.0 shortly. So what ahead is the future trend that I perspect is you will be finding cloud-based CAD platforms wherein there won't be any specific need of a high-end workstation, high processor at the designer's end. The virtual labs that are available at EIT are classic examples of these cloud-based CAD platforms. There would be AI and machine learning integrated with CAD/CAM systems. AI and machine learning means I had created a one particular component which used basic rough cutting and finishing cutting cycles. Now, if I'm having similar kind of two-axis jobs, which require some different operations, this was basically step turning, then it was basically having a facing cycle, and it was having just knuckle creation. But in future, if I am having some grooving, some parting or threading, then machine learning and AI tools can help me in doing this, wherein I can train the model and the trained model can be used for the future new jobs that are coming to my virtue. You can also have AR, VR, and immersive design technologies wherein virtual prototyping can also come into existence. It is basically, this is already existing in the market. Already now people have started integrating this CAD and the analysis parts to directly 3D printing and additive manufacturing. For prototype creation, many people use only 3D printing. Whereas when you talk about CAD, again, it can be IoT and real-time machine monitoring, wherein I can monitor the machine in India, and if the machine is in Australia or US, I can govern it with the help of real-time monitoring. Again, cloud-based CAM manufacturing collaborative machining is the way ahead. Already, twin digital manufacturing and digital twins are also into the market. AI-driven optimization can also improve a lot. So this is all what I perspect is the future trends. These are few of the references that I take to from which I took help in order to basically prepare this presentation and present it before you. With this, I am ending with my presentation. And Maria, now we can open up the session for question and answers.
Thank you so much, Dr. Shaw. Before we get to the Q&A, which if you could pop over to the Q&A uh, board and scroll to the very bottom to get to the first one. Let's go back here for just a second. For people who need to leave due to time constraints, I just want to make sure that you have the QR code that you can use to download your certificate. I'm sorry, to download the survey, which you will submit to receive your certificate. I'm also including a link to that in the chat. So you can use your phones. Those of you who are on your phones, you can use this QR code, and the link is in the chat right now, the regular chat, not the Q&A chat. Please click on that. The time frame to do this is 24 hours, so you need to do this today if you would like to get your certificate of attendance. If you don't care, then that's okay. But after today, it will no longer be available, and we don't award the certificates if you don't fill out the form. In addition, it takes about 4 business days for us to process everything. This is manual and not electronic, so please do give our team time to process your request for their certificates. And after 4 business days, if you have not received it and you filled out the form, get onto our live chat or reach out to your local course advisor, and we will assist you in getting that and getting your certificate. Okay, and let's jump over to Q&A.
Maria, could you spare a minute or two to just brief the audience about the courses which covers this topic?
Oh, certainly. So we do have, and this will be sent to you in the email that you'll receive within 2 business days with the slides. But we have several courses that cover this topic. Professional certificates, which are short courses. They're 3 months long. They are professional development courses. There are 2 of them, the Professional Certificate in Mechanical Engineering and the Professional Certificate of Competency in Industrial Automation Engineering. Then we have 2 advanced diplomas, one in Industrial Automation Engineering and one in Mechanical Engineering Technology. These are our 18-month accredited vet vocational courses, highly practical courses that will cover these topics. And then we have a graduate diploma of engineering for industrial automation. We actually have a Bachelor of Industrial Automation too, but I think the online Master of Industrial Automation more broadly covers this topic. The links of these will be sent to you guys, so look for that in your email. Are there any questions regarding our courses? I'm happy to answer them. I will also be putting my email into the chat, so if you want to directly email me with any questions that are course related, I can't answer the technical questions, that's Dr. Shaw, but any course or school questions, I'm happy to answer those, and I will send you my contact details so that you can ask those questions.
Thank you, Maria. Should I now take up some question and answers which are posted
Yes,
in the chat?
please.
Yes.
Let's get to the Q&A.
Okay, but there are some questions posted in the chat. I would now request the audience to post them into the Q&A session, but I can just read out some queries that has been posted. Mohammed asks me about which software is better. Is it CATIA? It is Creo? It is SolidWorks? I would just like to say that uh, all of these softwares have got good functionality. These softwares come up with a newer version every year, and they take up the tools newly invented by the competitor and put them into their software, and they come up with a newer version. You can go and learn any software. Learning the different software is matter of one day. You just need to identify where the particular tool is. Some tools will ask you to first create a section and then add material in order to create a solid model. Somebody will ask you to first create a or add up a material and then do that. I mean, somebody will ask you to catch ear like this. Some tools will ask you to catch ear like this. So any tool which is at your resort, you can start learning that. Learning a different software when you come across that is just a matter of 2 days, not more than that. Hope I have answered your question on that. I'm now moving to the Q&A tab. At present, I do not see any questions in the Q&A tab. Let me just move back to the chat and
Oh no,
find
there's
out.
several questions in there. I'm not sure why you're not seeing them, but the first one came an hour ago when you first started. Dr. Shaw, could you explain computer-aided design and manufacturing, CAD, CAM, what it is and how this technology is transforming engineering and production processes in the modern industry? I'm not sure if that's a short answer for that one.
Yes, basically, I tried to cover up that in my entire session. But to sum up, computer-aided designing nowadays helps quite a lot. Now, nobody goes basically with the conventional type because you know that you will be having a design team. Designing is not just a work of individual. What the design team does is they will be segregating the entire system into parts, and the parts are being assigned to various teams. They come up and collaborate in bringing up the entire system together, wherein when you are bringing the system together, you are able to track the or basically you are able to edit it. You are basically available for changes if any changes are suggested by the engineering tool. Coming up to computer aided manufacturing, it is the most versatile tool nowadays just because the conventional machine tools that we were having are basically, just to give an example, it was just basically giving you the tolerances, if that is open tolerances, they can machine up to plus or minus 1 mm. But with this invent of this CNC machines, you can now talk in terms of tolerance, and tolerance as high as 10 microns, 20 microns. If such machining processes are to be employed, such components critical to aerospace are to be created, then you have to obviously employ CNC machines where the design would be the input from the output of the CAD and then take it to manufacturing.
So Luis asked that question. He had another question as well. What are the technical and institutional challenges of integrating blockchain with other Industry 4.0 technologies, such as the Internet of Things, cloud computing, and data and analytics?
Okay, so when you talk about blockchain, it entirely covers the cloud computing, big data analytics. Blockchain is basically a result of critical analytics done. And this critical analysis is done with the help of tools like OpenGI tools, or they might be imposing very critical tools specifically meant for data analytics. And that input is then taken for further processing to blockchain. Blockchain, I mean, just a very good example of blockchain is this crypto. The cryptocurrencies work on the blockchain system. So applicable to our manufacturing processes, there are many applications of blockchain. To depict some of the applications, they are meant for inventory management and tooling control and fixturing control. You might be having n number of components designed in the machine. Blockchain will help you identify fixturing which can be used across various number of components, thereby avoiding the costly inventory of the tools.
Um, and the next question from him, there are several from him. At what stage does the Shigley model, at what stage of the Shigley model is it most critical to involve multiple disciplines such as engineering, industrial design, and market analysis?
Maria, why can't I see the Q&A tab?
I
Because I
don't know.
didn't.
I know earlier
Hmm.
it wasn't loading for me and I had to keep going back to it. So I don't know if it is just a broadband issue, like your internet may not be allowing everything to be running at
Okay.
once,
Because
but
I
it's
did not exactly get his question. It was pretty long to understand. I mean, we can also share them my email ID and I can obviously reply them offline also.
okay. He was just wondering when you involve other disciplines when you're on the Shigley model.
On the, on the
Shigley, Shigley.
Okay, okay, okay. So this was basically the model that I best feel that it is suited for a design. If you refer standard references, if you refer open literature available in the market, many authors have suggested many models. But to me, the Sigley model that I presented, the first two stages, that is identification of the need and then definition of the problem, are very critical to both the parts. That is the conventional design as well as the computer aided design. And there can be no replacing phenomena or no replacing tools to this, because you need to identify the need and then define the problem. Just because, as I told you, definition of the problem will clearly help in understanding the problem to the entire design team. Each and every design person will have the knowledge of what is to be done and what his specific role will be. Moving ahead, the computer-aided design comes into picture at the third stage, that is the synthesis stage. The synthesis stage is the stage where CAD tools comes into picture, and synthesis is basically done with the help of this geometric modeling softwares. So at the third stage, there is huge difference between the conventional Sigley model and the computer-aided design Sigley model.
So same things, Shigley model. What criteria, sorry, I'm getting things popping up. What criteria should be considered in the evaluation stage to decide whether the design can be approved or whether it's impossible to meet the specifications? So when is it
Okay,
a go,
okay.
no go?
I was half expecting this question, and it's a very good question, which I think all the audience should know about this. He is just asking that after the synthesis stage comes the evaluation stage. How do we qualify that the entire system goes for evaluation and it is passing the evaluation, moving further to either optimization stage or the manufacturing stage? So I can cite a few examples to elaborate this point. Actually, when we are specifically designing, be it a physical prototype, before invention of CAD softwares also, we normally used to impose certain factor of safety. This factor of safety is imposed upon a component depending majorly upon the loading conditions. If it is, say, pure tensile or pure rotational, or the loading is as simple as the compressive or tensile load, the factor of safety imposed is around 1.2 or 1.5. But for critical components, like critical components which are undergoing fatigue loading, which are undergoing creep loading, wherein the failure chances are more than expected circumstances, at that time, depending upon the loading condition, the factor of safety is added to it. So coming back to the point, once you are designing and analyzing it, say for example, if the computer component is subject to pure tension load, you analyze the problem, you come up with the some results in form of a stress strain diagrams or stress diagrams or von Mises plots. You will be having plots in form of a colored contour, just like that I shown you. And that colored contour will be having blue bands, yellow bands, green bands, red bands, etc. Most of the software will be depicting the dangerous or the critical part by red contour. So you need to compare that red contour the stresses in that region with the material properties. Now, when I say material properties, if it is pure tension load, you are supposed to consider the tensile strength of the material. It is pure compressive, you need to consider the compressive strength. If this working stress is exceeding the material properties, it means that it is going to fail and you need to redesign it. But if it is withstanding that particular load and that critical or the red portion stresses are way below the material properties, you can move ahead and classify that that particular component analysis is passing the loading conditions. But again, into quotations, you are supposed to capture the boundary conditions properly. You should know the type of loading conditions, the point where that specific load is to be applied, the part where it is constrained, etc., etc. Even we need to identify the types of joints and something like that. Hope I have
So
answered your question.
he also asks, how does the use of CAD contribute to increasing the accuracy and reliability of projects in the mechanical engineering, architecture, and manufacturing sectors?
Mechanical engineering, architectural, and manufacturing sectors. Okay. So uh, I will just quote an example of manufacturing and that can be elaborated to architectural and various other aspects. I just talked about geometric modeling, but there is now a growing trend of using parametric model also. Parametric model means, as you are aware, these tools are employed at design stage and design is bound to change. It is never possible that the design will make it route to the final stage right from the word go or for the first stage itself. Let us take for an example, we are designing an IC engine and the IC engine needs to generate certain amount of power, which I am doing it with a parametric model. Parametric model, now I am directly discreting the entire engine to small component assembly. Let me say the piston and cylinder assembly. I have designed a piston with certain diameter. I have designed a certain inside diameter of a cylinder. Obviously, there is a clearance between that two, which is very low. If my piston diameter is, say, for example, 200 mm, the inside diameter of the cylinder would be 200 plus some value. At certain point of time, I found that the power is not sufficient and I need to increase the number of cylinders or I need to increase the size of the cylinder and the piston. So how that now I come to your question, answer of your question, how exactly it is implemented. I can entirely design this IC engine based on the parameterization. That is, if I say 200 diameter of the piston as D1, I will not give D2, I will not give the dimension to inside diameter of the cylinder. I will give it a dimension in form of diameters or the parameter in form of the diameter of the cylinder. That is, I will say D1 plus 0.5 m. So at certain point of time, I need to change my design. When I will change the diameter of the piston from 200 to 220, automatically the cylinder will change. I need not to take care about all the assembly line down line. The piston and cylinder is one example. The piston rings, the gudgeon pins, the crankshaft, everything needs to be changed. But if I am designing this by parameters, thus by changing or controlling one critical part or the dimension of the part, I can change the entire assembly down the line. So that is how CAD tools can be effectively used in today's manufacturing scenario.
So Mohammed asks, what is one common mistake you see new CAD CAM users make, and how do we avoid them?
Both of them are different. People do mistakes in computer aided design. People do mistakes in when importing it into computer aided manufacturing. But the mistakes that I basically find is when you are, this was a very simple job because the time was limited. So I took a very simple job having few operations. You are having a complex job and you are importing it into a CAM software. This CAM software is basically driving a CNC tool. Now you know that CNC machines are equipped with ATC, that is automatic tool changer facilities, and APT, that is automatic pallet changer facilities. These automatic tool changer facilities would have or would house, depending upon the capacity of the machine, it can house up to 35, 36, 39, more than that number of tools. Identifying these tools, say for example, the tool changing magazine has having 36 tools. So all of the tool stations would be numbered as T01, T02, T03, T04, T05, T06, etc. Still, the artificial intelligence is not built up in such a manner that the machine will identify that the threading tool is located at 6 number position. The turning tool is at tool number 1. The parting tool is at tool number 14. The intelligence has not been developed. It is the user who needs to have the knowledge of the This is one example that I'm citing. He needs to have the knowledge of what tool is being located at what tool station. So when that particular tool has to be brought, that particular tool station has to be called. So moving ahead, as I shown you, the future trends, AI and ML can help the machine in identifying the operation, and depending upon the operation, it can search the tool required to do that particular operation. So this is one common mistake that I see.
Um, Oru, and I believe that this was part of your presentation where you listed some FEA softwares. He wants to know which of them is the best for mechanical engineering.
Uh, as I told you, nowadays the modeling software in this competitive market like SolidWorks, CATIA, Creo, all of them are giving you basic facilities of doing basic analysis. But the entire market share, or say 90% of the market share, when we talk about CA tools, is governed by ANSYS. Just because ANSYS is a multi-physics software, it can do n number of structural and non-structural analysis. Structural analysis may it be static, dynamic, vibrational analysis. Even it is now capable of doing acoustic analysis and electromagnetism. When we talk about non-structural, the domain has got heat transfer, fluid flow, all this type of analysis is taken care by ANSYS. So yes, there was a simple answer to the question which was posed to me that which software should I learn. It was as simple as that. But when it comes to analysis software, one software that covers the entire domain of the analysis is ANSYS, and 90% of the market share is governed or covered by ANSYS. Though there are specific tools, like say for Abacus. Abacus is very powerful in manufacturing simulations. If you are going for specific sheet metal industries, that is forming operation, a software called Hyperform has got more capabilities. But Abacus or Hyperform are basically local to that particular operations or that particular analysis. Whereas ANSYS will provide you multi-physics, multi-domain analysis. Even you can do much more in that, that it is if it is coupled field analysis, and that is, I mean, obvious. Say for example, a ball bearing is normally subjected to the torsional load of the shaft. The outer casing of the ball bearing is constrained in the bearing housing, whereas the inner race will be rotating with the shaft. But upon usage of time, when the lubrication goes away, there would be also problems of heating up, overheating of the bearing. So there are two conditions where the component is loaded upon. One is the structural load, and with that the thermal load, because it is getting heated up. So this is coupled field. When more than one type of analysis is to be covered under one roof, it is coupled field. So ANSYS is even capable in doing coupled field analysis. So yes, my personal views that ANSYS has more capabilities when talking about analysis.
So Jared had a question about AI and the what humans are going to be left to do. So he said specifically how much of these processes are going to be computer automated or AI automated, and what will be what will be left for humans.
Okay. So, I mean, that is a general question which we are always posed when we talk about OpenGI or any, be it any AI tool that we are using, that normally people are now worried that where is the job left for a programmer, core programmer. But believe me, these tools, AI tools, have to be taught. And this teaching phase will always require human interference and an engineering interference, because a job is always unique in itself. So in order to train the model or train the AI model, you will always require a qualified engineer to do that. It's not that the component that you are manufacturing today will not undergo any kind of changes. Tomorrow you will be coming across some various other components design which the machine is not capable or it has not learned that. So it is the task of the job of the engineer to teach them and build up AI into the machine tool. So I don't presume that the role of an engineer will anyhow with the advent of AI will go away. Because
Um,
still, yes, yes,
no,
please.
go ahead, please, 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 go
Because
ahead.
still, as I told you, that there are n number of process plans, n number of machining operations to be done, n number of tools to be taken. So it has to be trained depending upon the model. And CNC machines are basically not mass production tools. Nobody use a CNC machine for mass production. They are used for ultra critical jobs which have got tolerances in the range of 10 microns. So for such critical jobs, yes, you will be always having new type of job, new type of machining challenges, which obviously needs to be trained. And it is not that because this training goes on and goes on.
Um, so I'm going to stop the questions here because it has been 30 minutes past our time. You said you'd be willing to share your email so people could send their direct questions directly to you. Are you amenable to that, Dr. Shaw?
I will be more than happy to do that,
Would
Maria.
you mind typing that in the chat for everyone?
Yes, yes,
And
sure,
I
sure.
do apologize that we couldn't get to every question, but there are still well over
No,
10
but
questions left, and there some of them are quite involved. So please do direct your technical questions to Dr. Shaw. I have included my email in the chat as well. If you have any course-related questions, please, please, please go ahead and reach out to me, and I'll be happy to answer those questions as well. If you want to know who your course advisor is for your region so that you can talk to somebody in your time zone, you can reach out to me and ask that question, and I will make sure that you get their information too. Thank you again, everyone, for joining. Thank you, Dr. Shaw, for a great presentation.
thank you
We
so
appreciate
much.
your time today, and I'm going to end this now, and I hope
Uh,
everybody has a great.
is my email ID visible in the chat
Yes, I
box?
saw it pop up.
Okay. Yes,
Yes,
yes.
thank you
Okay,
so
fine.
much. I will, everybody, as I said before, please give us 4 business days to get those certificates out to you, 2 business days to get the slides and the link to the video out to you. Thank you again, and I hope everybody has a good morning, afternoon, or evening, depending on where you are in the world. Bye for now.
Thank you, Maria, for helping me out.
Oh, my pleasure. My pleasure.
Thank you so much. You are a very good audience.